Good afternoon. So my name is Gerry, and I will be presenting OTTER, Efficient Multi-WAN Transport for 5G. This was work done when Mary, Yiming, and I were interns at Microsoft, alongside our mentors, Sharad, Ryan, Rachee, and Victor Bahl. We've all since graduated, but I'm super excited to be here today to tell you about what we built. So I want to start by discussing two major transformations currently underway that are enabling the next generation of telecom applications. The first is 5G New Radio, which is wireless technology that powers extremely high-performance last-mile access. It introduces new frequency bands and innovations in radio multiplexing and RAN protocols to enable both new and diverse capabilities like multi-gig speeds for high-resolution video streaming in virtual reality, sub-millisecond latency for applications like self-driving cars and online gaming, massive connectivity for IoT devices, factory robots, and cell phones, and even 5 nines worth of availability for critical apps like remote surgery. The second transformation, which is happening in parallel with the deployment of new radio, is a process known as cloudification. Now, this is where telecom operators have partnered with cloud providers to migrate their network functions and application servers into the cloud. So why is this happening? Well, historically, operators built their cellular networks by buying proprietary boxes from equipment vendors on which they ran their network functions. But this can be very expensive, hard to maintain, and hard to scale. Today, there's a really strong push to virtualize everything. Network functions and application servers have now started to run on commodity hardware in cloud data centers and edge sites, making it much easier to deploy and manage 5G networks. So by leveraging the flexible deployment and statistical multiplexing benefits of the cloud, operators can be much more flexible about where user flows are served from and can also easily scale up and down their networks based on demand. Now, I want to emphasize that neither new radio nor cloudification is just a bet on the future or something that could happen in the next 5 years. Standalone new radio is already being deployed, and cloudification is already underway. And we can find plenty of press releases and demos that showcase new partnerships and new milestones being reached, which I've shown a couple of examples here on the slide, but these are all currently happening. So the interesting thing about cloudification is that 5G traffic can now traverse not just one, but 2 wide area networks, an operator WAN and a cloud WAN. User equipment would first connect to cell towers in the operator's network, and traffic can land at one of potentially many edge sites in the operator WAN, or it can terminate at a 5G core in a cloud edge, or even one of many cloud data centers. But this paradigm introduces a lot of pressure on wide area network performance. So traditionally, the last mile has been the primary bottleneck in end-to-end performance, but with the improvements made by new radio, the WANs have now become the bottleneck. So now there's an expectation for multi-gig throughputs per user hitting cloud services. Sub-millisecond over-the-air latencies now have to take additional dozens of milliseconds to traverse 2 WANs, and there are also much higher reliability guarantees that the WANs have to meet for certain applications, in some cases even mandated by regulation. The good news is that with cloudification, both the operator and the cloud provider have a shared business incentive to provide end-to-end quality of service to 5G traffic. And this presents a really unique opportunity to optimize across 2 wide area networks, where we can take advantage of the path diversity and differing service demands of 5G traffic to make smarter transport decisions. So let me give a concrete example to demonstrate what I mean. So here I've abstracted the 2 WANs into 8 nodes, the operator on the left and then the cloud on the right. The edges are labeled with hypothetical latencies of the link, and the dashed lines represent peerings. So let's say we have a flow with the source on the bottom left and a destination on the upper right that wants a latency of under 60 milliseconds. If we use the default routing within each WAN to minimize the latency on its own network, the operator would choose the lowest latency path to egress at node N3 with a latency of 20, and then the cloud would choose this path with the latency of 80, leading to this path with an end-to-end latency of 100. But there's an even better path that exists with a much lower end-to-end latency of 5050. So since our flow here is latency sensitive, it makes sense to place it on this path. But what if this flow didn't care about latency? Maybe it's part of a streaming video application. Then it might actually be more beneficial to allocate it to the bottom path and then save the available bandwidth on the top one for flows with more stringent latency requirements. And it's not just about which path to take to a given destination. There are also lots of decisions we can make around which destinations the flows should be routed to in the first place. So for instance, which edge site should we choose to deploy our network functions in? Or which cloud data center should we choose? And this adds a lot more complexity to the problem, but it also offers more flexibility from cloudification, again, made possible by the aligned business incentives between the operator and the cloud provider. So being able to make these multi-WAN transport decisions at scale is the challenge. So to summarize the problem, the next generation applications enabled by 5G new radio and cloudification need end-to-end quality of service. Transport can now include two WANs, an operator WAN and a cloud WAN, but inefficiencies in the wireline paths can negate the benefits of new radio. And then default routing over the WANs just doesn't support the diverse fine-grained service objectives of 5G traffic. So this is where OTTER comes in. It is a system for efficient transport and resource allocation across both an operator WAN and a cloud WAN for 5G flows with differing quality of service needs. It has three main technical components. The first is a controller, which accepts 5G flow demands from using standardized network APIs, and then runs an optimizer to decide which flows should be allocated to which paths and which destinations. An orchestrator then manages the cloud resources and then implements the forwarding mechanism in an overlay network to steer traffic along the paths computed by the controller. And then finally, we have a measurement coordinator that takes performance measurements along the overlay and then feeds this information back to the controller. I'm not going to talk too much about the measurement aspect in this talk, but you're welcome to read the paper for more details. So how do we optimally place 5G flows with different quality of service demands across two WANs? We can express this as an optimization problem where the inputs are a set of flows and a set of paths. Now, a flow is typically represented by a source, a destination, and a bandwidth demand, and a path is typically represented by a source, a destination, and a set of constituent links. Now, if you're familiar with traffic engineering, you might recognize this as a standard multi-commodity flow problem. But with OTTER, we extend this formulation so that each flow is represented by a source and a set of potential destinations. And this is what lets us further optimize the path performance by adjusting the destinations of flows and deploying compute resources in more optimal locations. Again, this is leveraging the deployment flexibility that cloudification brings us. We also encode the service demands and resource requirements of each flow as a vector of demand functions and resource requirements, and then the paths are also annotated with performance characteristics supplied by the measurement coordinator. Our objective function is then as follows. We want to maximize the amount of bandwidth a flow F is assigned to a path P, weighted by the degree of service demand satisfaction on that path, normalized by the bandwidth demand, and subject to destination resource constraints. And this last part is important because the resources available at an edge site could differ dramatically than at a data center. Intuitively, what this expression means is that we want to allocate as much bandwidth as possible while satisfying the service demands of individual flows. This is a linear program, so it's quite efficient to solve, but unlike typical wide area network traffic, 5G traffic can be much more dynamic. So depending on the size of the network, we actually won't be able to run the full optimizer on every new flow. So for practical purposes, we greedily allocate flows on demand to paths with the best demand satisfaction, and then periodically run the global optimization, potentially shifting flows to more appropriate paths. And we found that this was a reasonable trade-off that still provided really good performance. All right, so given the routes computed by the controller, how do we steer traffic along these multi-WAN paths? Our solution is a multi-WAN overlay using only native cloud functionality. So what I mean by this is that we can deploy our own VMs, VPN gateways, and other components in different regions around the world, and then program forwarding rules using only what's possible using publicly available cloud interfaces. So with this overlay design, there's no need for explicit cooperation between the two WANs, so this prevents, so operators can avoid cloud lock-in. There's also no need for significant engineering effort to exploit path diversity, And then we can also easily scale up and scale out by simply deploying more cloud resources in more locations. So here's a diagram of an actual overlay that we built across the continental United States. It's a bit hard to read, but each box represents a cloud component like a VM or a private VNet, and then the lines represent connections between them. So this topology spans 8 different cloud regions and represents a large 5G network built by a national level operator and a major cloud provider. So I'll give an example of overlay paths with different performance characteristics that we were actually able to achieve on this topology. So these are real measurements that I've mapped to our 8-node abstraction. So for the same source and destination, if we took the default path where the operator handed off the traffic at the nearest peering point to the cloud WAN, we can achieve an RTT of 40.6 milliseconds and a throughput of 13.6 gigs. However, OTTER can easily send traffic along an alternative path with different trade-offs. So for instance, this one has much lower RTT for a similar throughput. And then this path has a much higher throughput, but also a worse RTT. So the point that I want to make is that OTTER is able to offer a choice among paths with different performance characteristics to better optimize for the differing service demands of 5G apps. And this isn't just a cherry-picked example. So here are the overall results across all source-destination pairs. We have a lot more figures that go into way more detail in the paper, but I'll highlight some of the top-level results now. So with OTTER, we could increase throughput by 13% on average and 136% in the best case. We could reduce latency by 15% on average and up to 56% in the best case. And in terms of bandwidth allocated, OTTER can achieve 25 to 46% more bytes allocated with higher service demand satisfaction compared to greedy baselines. So in summary, I want to make the observation that new radio and cloudification are already happening. Access links are getting so fast that the end-to-end performance needed by 5G applications are being bottlenecked on inter-domain WAN paths. So with this, we introduced OTTER to help recapture some of this performance by co-optimizing both the paths and the destinations of 5G flows with diverse quality of service needs, and then implementing this using a scalable multi-WAN overlay that unlocks inter-domain routing flexibility. So thank you for listening, and happy to take questions.